A region in the form of an equilateral triangle in xy plane of height L has a uniform magnetic field B pointing in plus Z direction. So in this question there is a region, a triangular region having magnetic field in outward direction. So that region is shown here. So this is a region. A conducting loop. So this PQR is a loop, conducting loop in the form of an equilateral triangle of same height L is placed in xy plane with its vertex at x equal to 0. So this is the vertex. At t equal to 0, the loop starts entering the region of magnetic field with a uniform velocity v along the plus x direction. So this direction is x. So this is loop starts moving in x direction. That is, it starts entering into this magnetic field. The plane of the loop and its orientation remain unchanged throughout its motion, and we have to find EMF as the loop moves as a function of time. So this is the question. First, consider an equilateral triangle making 60-degree angle at its vertex. So it's shown in green color, and drop a perpendicular from the vertex to its base. So from this vertex we have dropped a perpendicular on its base, and let its length be A. This will divide the triangle into congruent right angle triangles. So this line will divide this whole triangle into two, and both these triangles are 90-degree triangles, okay, making 30 degree. So obviously this angle 60 will be divided equally, so it will be 30 in each triangle. Now consider one of these triangles. So suppose you consider this half, the right one, and this side which is opposite to this angle 30 will be A tan 30, that is A upon root 3. So the area of this triangle will be half base into height. So half base is twice of this side, so it is 2 times A root by root 3, and into height, that is A, so it is A square by root 3. And I'll be using this formula again and again in this video, so please remember this formula. If we have an equilateral triangle of height A, then its area is A square by root 3. Okay. Now we'll consider two cases. One, when this triangle, this moving triangle has moved a distance less than L. So this is the first case when the distance moved, that is x, is less than L. So this total distance, so apex has started from this position, and it has moved down to this position. So this distance is x. This is line of symmetry. So it will divide this distance into two equal parts, x by 2 each. And the area of this moving triangle, which is in the magnetic field now, is this much, these two small triangles. So we have to find this area, the total area of these two triangles. First we find area of one of these two triangles. So this is this green one. So its area will be, remember that formula which we derived earlier, height square divided by root 3. So this is the area, and this is the another part. So to find the total area, we'll just have to multiply this area by 2. So that we have done here, it is multiplied by 2. And the flux is B times total area. So simply this area is multiplied by B. So this is flux. And to find EMF, we have to differentiate this. So when we differentiate this expression, so EMF is minus of d phi by dt. So there is a minus sign for that. And B and 2 root 3, these are constant things. So they are written just like that only. When x squared is differentiated, so it will give 2x into dx by dt, and dx by dt is nothing but velocity of this moving triangle. So this is the expression for EMF. Now consider the case when the distance moved by the moving triangle is more than L. So suppose this moving triangle has moved a distance x, and x is more than L. So here in this figure, as you can check, so the earlier vertex was here at the starting of the movement, and now it is at this position. So it has moved down to this distance, which is x, and it is more than L. This you can verify. This line is line of symmetry as usual. This distance is x, this is L, so this will be x minus L. Now the area of interest, the area through which the flux will pass, is shown here. So this is the area common to both triangles. So we have to find this area. So line of symmetry is dividing this area into two equal parts. Suppose we find the area of upper part first. So that can be done by first finding the area of this total red triangle. So area shaded in red is height is square by root 3, and height is half of this total x. This is line of symmetry. So it is x by 2 square by root 3. And then we have to subtract the area of this upper small triangle. So the area removed is this upper triangle. So the same formula, height is square by root 3. So we have to decrease from this total area, the area of this removed part. So that I'm going to do. So okay, I have decreased this area from the total area. So this is the area obtained. This is the area of this red part. And since there are two such parts, simply we have to multiply by 2. Flux is B times total area. So it's as simple as this. And the EMF is minus d by dt of total flux. And then we have to differentiate this. B over root 3 is just a constant. This you can check yourself. ds by dt is velocity. So wherever dx by dt comes, it's written as velocity there. So finally we have EMF varying as this. So in both the cases, you can check that the EMF is proportional to x raised to power 1. So it is changing linearly. So the graph of both the parts should be a line graph. So, so it's a linear graph. This is the graph of the first part when x moved is less than or equal to L. At L, the EMF was minus BLV by root 3. This you can verify. So this was the expression minus BLV by root 3 at x equal to L. And at x equal to 2L, this EMF is 2 times BLV by root 3. Again verify this. In this expression, if you put x is equal to 2L, you'll get 2 BLV by root 3. So the graph will be having two parts, two linear parts. So the graph will be having two linear parts as shown. Okay, thank you.